Okay, more optimization. This is the last chapter where we're doing comparative statics, where we're doing differentials and derivatives and all that. And soon I will finish up by doing some dynamics. Really exciting. All right, so we're doing something now called nonlinear programming. And the key to this, the trick to this, is something called the Kuhn-Tucker conditions, which were invented by two guys who cleverly their last names are, Kuhn and Tucker. And this is not some wild new technique. This is like from the 50s this was invented. Okay? If you take management, if you go take management courses, depending on what you're doing in those courses, you might do something called linear programming, which is very much like what we've been doing, where you have not one constraint, but a bunch of constraints, and then you figure out the best way to deal with all these constraints to optimize your firm's business based on these constraints. And it's very similar to what we're doing. In fact, if you had taken this class a long time ago, there probably would be a chapter on linear programming in there too, but we economists don't generally do that anymore. Okay, so let's remember back in time, and we would do a problem like this, and I mean by time like the last chapter, right? So we're going to maximize our utility function subject to our budget equals, pxx plus pyy. Now, it should occur to you that there's a problemo with this. There's two things we didn't do with this. One is, and what we should have done, is put a restriction on this that says both x and y are greater than or equal to 0. It doesn't make any sense for us to be buying negative quantities, and so we should have put some kind of restriction on there that x and y have to be greater than or equal to 0. All right, that's not the big problem for the most part in this. The big problem for the most part in this is this. I have to spend, this constraint says, I have to spend all my money on X and Y. Now, we live in a world where there's diminishing marginal utility. Diminishing marginal utility. You would think by now I'd be better at writing with my Apple Pencil, but no. So maybe as my budget gets bigger, as I get richer, as I get more money, maybe I reach a point where the utility from buying more things is just low. And I'm better off not buying things. I'm not increasing my utility. I'd rather have that money sitting there, right? I'd rather have savings than buying stuff. Okay? So this might not actually be generating the answers we want because it requires me to buy, right, with all my income. So the easiest way around that would be to say, well, easy conceptually, not easy in terms of necessarily solving, but I have two goods, X and Y, and I'm subject to B equals PXX plus PYY plus S. Now S, because I just used the word savings, you might think that stands for savings, but no, S stands for slack. And what we do in regular linear programming is basically this. We add a bunch of what are called slack variables. We add room so that we don't have to use our entire constraints. And that way we find out what constraints are really binding on us. We've lived in a world where there's one constraint. But what happens if there's, 3 constraints, 4 constraints? Well, it turns out that all of a sudden becomes a lot less important, and the optimizing solution tends to be defined by the constraints. Okay? And we've sort of talked about this before. In a lot of times in models, you create all these assumptions, and by the time you're done assuming stuff, the assumptions have determined the outcome of the problem. Okay? We see this all the time in articles that people write, and you're like, dude, especially in macro, right? I'm a macro guy. In macro, it's commonplace for people to assume stuff away. I actually wrote my dissertation on multinational corporations and taxing multinational corporations, the optimal way to tax corporations that operate across different countries. Okay? Most of the models of giant multinational corporations assume perfect competition. Well, once you assume perfect competition, you take away a whole bunch of outcomes which are probably the real world outcomes. You've assumed them away. Okay? We do it, but we don't like to do that, right? That's not our thing. We don't want to assume away all of these outcomes. In linear programming, they put these slack variables in there so that just because you assume that we spend all our money doesn't mean it actually has to happen. And this way you find out. And what happens is you'll have some constraints that maybe this constraint is binding and maybe these 3 aren't. And therefore this constraint being not binding is the one that's holding you back. And now you have to figure out, well, how are we going to get that one? Okay? All right. So the simplest version of nonlinear programming is to say that we have y as a function of x subject to x is greater than or equal to 0. Okay? This is the simplest version of these things. And so what we get in that case, what we're saying is that we have what's called a feasible space. And in this case, that feasible space is all of this, right? Everything out here. Yes? This area is not in the feasible space. This area, there's actually 4 quadrants here, right? No feasible space over here, no feasible space. We've taken the world's infinite, but we've taken a quarter of infinity and marked it off and said the answer has to be in here somewhere. Okay? So we've changed our world, so we only have positive x's and, well, we might have negative y's, but usually that means we don't have. Okay? So we have our feasible space. Then we have possibilities. So let's suppose we just have a function that looks like that. Okay? If that is the best place, that's on the edge of the feasible space, right? That's our edge. That edge point is called a boundary solution. And the rest of the ones, all the ones in here, are called interior solutions. Now here you are saying, why do I need to know this? Well, the answer is when we do these problems, We generally don't solve them the mathy way. Okay, and we'll get back to y as a function of x. Y equals x squared, x greater than or equal to 0. Okay, well that's easy to solve, right? I can solve that mathy-wise, right? I can say dy dx is 2x, right? I optimize that by setting it equal to 0. That means x equals 0, and that fits my constraint. In fact, that would be what? X equals 0. That's a boundary solution. Okay? Yeah? And because the second derivative is equal to 2, which is greater than 0, that's the minimum. Well, what if I want to max this? Well, then I have another problem. Okay? No? Righty then. So, we're going to create problems that look like I want to max my utility, which is a function of x and y, and we're going to say that's subject to my budget is greater than or equal to pxx plus pyy, and x and y are both greater than or equal to 0. Now I technically have 3 constraints. Okay? I have 3 constraints here. 3, you can count them. 1, 2, 3. Which before, if I made them all equal, I would just be solving for, right? I would just be solving for the constraints where the constraints all meet, and that would be my point. But now, okay, now I can do some mathy stuff here, yes? Yes? Yeah. Okay. So, I could say, look, I want to max, max my y is a function of x1, x2, and x3. Subject to some g is a function of x1, that's a 1, x1, x2, x3, which is less than or equal to, some constant, right? B1. And I could have another g, right? Or I could have an h function. So I can have as many functions as I want, right? Call that h, right? And then I have an x1, x2, and x3 are all greater than or equal to 0. So I have this whole shooting match. Now again, what I could do is put some s's in here. I could put these slack variables in here. Okay? So I could say, I want to max, right? I have this function of x1, x2, x3, and then it's subject to g of x1, x2, and x3 plus s1 equals b1, and h of x1, x2, and x3 plus s2 equals b2. And now I can solve this, but I have sort of. And then I've got x1, x2, and x3 all greater than or equal to 0. These two things are variables. Now I probably have probably have more unknowns than I have legitimate equations, maybe. Yeah. I might not be able to solve this baby, okay, with those slack variables because I'm going to have a lambda 1 and a lambda 2, a lambda for each one of these, right? Yes? I'm going to have lambdas in here. Yeah? When I set this up, and I'm going to have variable and variable and variable and variable and variable and I got more variables than I got equations. Okay? So I'm not going to be able to do the old school solvey thing.